Let's look at sampling distributions. Before we get into that, first we want to talk about statistics and parameters. It's a little bit of a review from stuff we've done earlier, but one of the things that we did previously is estimate the population proportion from the proportion of a sample. And the proportion of a sample we called p hat. So just the p with a little caret thing on top. And then we estimated p. That's the value for the whole population, the parameter. So if we were studying, let's say, the entire school, the proportion of the school would be represented with p, and the proportion of the people in our sample, our SRS, or however we sampled, would be p hat. Same idea applies to estimating the mean. If we go out and ask 30 people to be part of our sample, that mean that we collect would be called x bar. And then if we wanted to talk about the whole population, so in this example, the entire school, we would be estimating what mu is. So that's the symbol that represents the mean for the entire population. And then same idea with standard deviation. When we're looking at a sample of data, we use SX. And then when we have the whole population, we use the Greek letter sigma. Now, whenever we're going out and collecting statistics, hoping that they can estimate a parameter for us, we always need to make sure that we don't introduce too many problems and we collect our data in a proper way. Most important thing is how we sample. SRS is the gold standard. Let's make it a nice little gold brick here. It's kind of the gold standard of sampling. Now, in reality, there are a few other ways that are basically as good, and the ones that we've talked about that would fall into that camp would be a systematic sample, where you pick a random starting point and then every 10th person you would sample, for example, or a stratified random sample. And we say correctly weighted because if you have different size groups, you have to make sure you pick the right number of people from each group. So if you do your stratified random sample correctly, it effectively ends up similar to an SRS. Now, besides choosing a good method like one of these three here, you also have to make sure you don't have too much non-response. If you have a very, very high non-response rate, it might almost look like a voluntary survey, and your data could be potentially skewed to only the types of people that want to respond. You don't want to have undercoverage where you end up missing people that should have been part of your sample but never got asked to participate, never even had a chance to be picked to participate. And you don't want to have things like intimidation or poorly worded questions or any other types of problems in the way that you collect your data that are going to cause your results to not be very meaningful. So again, we're using our statistics that we collect from a sample to represent the entire population. We're not going to ask everyone and do a census. We're only going to ask some people to collect our data. And as long as we do it in the correct way, we should be able to get some valid information. Shift gears for a second. We're going to talk about distributions. Go ahead, pull this up here so we can look at these one at a time. A distribution is the set of responses to a question. So usually if we're doing a survey, the distribution would be all the results that people have. Or if we are collecting data, let's say on animals, it would be the list of numbers or the list of categorical choices or options that we find. So a couple examples of that. If we have a qualitative distribution where we're using categorical data, then it would be the list of the options picked. So if you ask people to fill out their eye color on a survey, you might have one person say brown, next person say brown, next person say blue, next brown, next green, and so forth. And who knows what they're going to choose, but it would just be the different options that they picked. And you could then turn this into a pie chart or a bar graph or whatever. A quantitative distribution is where you have a list of numbers. So, for example, if you're looking at heights, you asked a bunch of people what their height was, and they all responded, oh, I'm 66 inches tall, 67, 60, 76, whatever they might be. That list is your distribution. So again, it's just a list of responses to whatever question you ask, whether it's what is your eye color, what is your height, or how long is the iguana, things like that. Now, the thing that we're going to talk about next is the distribution of sampling averages. And that's just a list of numbers. It's a list of averages from many SRSs. So I'm going to show you a quick example of the sampling distribution and how we get that. So here, there's our example about our population of adult iguanas. Let's imagine that this is the entire population right here. This list of numbers. There's 4 foot, 5 foot 4, 5.5 feet, and so forth, are the different lengths of these iguanas. So in order to do our SRS, I'm going to throw all these numbers into the hat here, shuffle them all up, and then I'm going to randomly pick a number. So I randomly chose, and whenever we pick from a hat and everything has an equal chance of getting picked, it's an SRS. So I randomly picked 1. But for this example, what I'm going to do is I'm going to actually pick 3 different lengths out of this hat. We're going to do a sample size of 3, and I'll explain why in a moment. Pick another one. Okay, 4.8, and oop, got the hat. 5.5. So these are the 3 randomly chosen lengths I just pulled out of this hat. And what I'm going to do is I'm going to take their average. So I brought up my calculator, and I'm going to add these numbers together and just do a simple average of them. Divide by 3 here. So my average of these 3 numbers is 5.4. So I'm going to write that number over here, 5.4. And I'm going to keep that. So I'm going to throw these back in, and now I'm going to do it again. I'm going to repeat. So I'm going to pull a new 3 numbers out of the hat. And this time I got 3.2, 4.7, and 5.5. Again, I'm going to take the average. I'm going to add them up in my calculator and divide by 3 because there's 3 numbers. And this time, it looks like I'm going to have a slightly different value. I have let's round it up to 4.5. So each time you do this, because the numbers you get are random, you're going to get different values. So you're not guaranteed to get the same average every time. It's going to be a little bit different every time. If you repeat this process for a very long time, you're going to have a very long distribution of all these different averages. And in this case, we're looking at averages of sample size 3. This distribution of averages, depending on the sample size you choose, has some very predictable properties. And so that's what we're going to look at in the next section is what are these predictable properties and how can it help us solve new types of problems.